So there are many ways to solve or to determine a voltage regulation of an alternator. So first is the direct method. So it is the one that we did earlier in our previous examples. And also we have the indirect method. So these are the following methods in indirect. We have the synchronous impedance or EMF method. It is due to Ben Eschenberg. Number 2 is the ampere turn or MMF method. This is due to Rutherford or Rutherford method. 3 is the zero power factor or Pottier method. So as the name indicates, it is due to Pottier. So all these methods require the armature resistance RA, the open circuit or no load characteristic, and the short circuit characteristic. So but zero power factor lagging characteristic is for Pottier method. First is we will discuss the synchronous impedance. So it is one way to solve the voltage regulation of an alternator. Synchronous impedance. So the following procedural steps are involved in this method. First is the open circuit current is plotted from the given data as shown in figure 37.33. So this one. We will plot the open circuit voltage of a given alternator. And also number 2, similarly, the short circuit current is drawn from the data given by the short circuit test. It is a straight line passing through the origin. Both these curves are drawn on a common field current base. So on the left side is the EMF, open circuit, and the other side is the short circuit current. So this will be your synchronous impedance. And then consider a field current. The open circuit voltage corresponding to this field is your E1. When the winding is short-circuited, the terminal voltage is 0. Hence, it may be assumed that the whole of this voltage E1 is being used to circulate the armature short-circuit current I1 against the synchronous impedance ZS. Therefore, your E1, which is the open circuit, is equal to I1, which is the short circuit current, times the synchronous impedance. So we can solve synchronous impedance equal to open circuit voltage divided by the short circuit voltage. So if we have a field current, which is this one, it will correspond now to the value of your E1, which is the open circuit voltage. And also, it will correspond to the short circuit current. And then we can solve now your synchronous impedance. So since RA can be found as we discussed earlier, synchronous reactance is equal to the square root of synchronous impedance squared minus RA squared. Knowing RA and XS can be drawn for any load and any power factor. So this is now your vector diagram, but I will not use voltage current as the reference. So I will use voltage as the reference. Okay, so pareho lang din sila pero depende kasi yung reference mo. So here, using this graph or using this vector diagram, you can solve the no load voltage. EO is equal to square root of V cosine phi plus IRA drop at the armature resistance plus the sine V sine phi plus IXS squared. So you can use this one, but I will not use this method. Either of the two na lang yung gamitin nyo, yung i-discuss ko in our examples or this one. Depende kung saan kayo mas komportable or mas naiintindihan. So finally, we can solve the voltage regulation. That is equal to the no load voltage minus the terminal voltage or output voltage divided by the output voltage V times 100 or terminal voltage. So we can demonstrate this method using example, synchronous impedance method. Example, find the synchronous impedance and reactance of an alternator in which a given field current produces an armature current of 200 amperes on a short circuit and a generated EMF of 50 volts on open circuit. The armature resistance is 0.1 ohm. To what induced voltage or no load voltage must be the alternator be excited if it is to deliver a load of 100 amperes at a power factor of 0.8 lagging with a terminal voltage of 200 volts. So our alternator has to deliver at 100 amperes, deliver a load at 0.8 power factor lagging. And so what will be its EO, no load voltage, given the following? The field current at short circuit is equal to 200 amperes. The field current at the open circuit, EOC or the E1, is 50 volts. And our power factor, theta, is 36.87 lagging. Therefore, we have a load current of 100, the magnitude, and its direction is the power factor, which is negative 36.87. So, negative kasi lagging power factor. We can solve synchronous impedance is equal to open circuit voltage divided by the short circuit voltage. That is 50 divided by 200 equal to 0.25 ohm. So we can solve now the synchronous reactance equal to the square root of synchronous impedance square minus, this is RA, not XS. So this is RA squared. That is equal to the square root of 0.25 square minus 0.1 squared, equal to 0.23 ohm. So this is now the vector diagram of a lagging power factor synchronous alternator. This is our reference, and the voltage is in phase with our reference. The voltage is equal to 200 volts. This one. The terminal voltage is 200 volts. It is in phase with the reference. And then our current lags by 36.87. And the drop in our resistance is in phase with our current. So that is IRA. And the IXS is 90 degrees with respect to IRA. 90. The sum of IRA and the sum of IXS is equal to your I synchronous impedance. Therefore, we can solve EO now will be equal to the terminal voltage, this one, plus etong green, plus vectorial sum of the drop in ZS. Or you can solve this one by terminal voltage plus IRA plus IXS. So, the same lang yan. Now, we can solve IZS equal to, our current is 100 angle negative 36.87 times the impedance, synchronous impedance, 0.1 is our RA, J, 0.23 is our XS. IZS now will be equal to 25.08 angle 29.631 degrees volts. The no load voltage now, or the induced voltage, is equal to 200 plus 25.08 angle 29.631 equal to 222.147 angle 3.1998. So this 3.1998 is nandito from the reference to EO, this one. So the magnitude of EO is 222.147. If we get the percent voltage regulation of this circuit, that is equal to EO minus V over V times 100. So 222.147 minus 200 divided by 200 times 100 is equal to 11.074%. Next example. From the following test results, determine the voltage regulation of a 2000 volts single-phase alternator delivering a current of 100 amperes at A unity, B 0.8 leading power factor, C 0.71 lagging power factor. So these are the test results in a synchronous alternator. Full load current of 100 amperes is produced on short circuit by a field excitation of 2.5 amperes. So we have a field excitation of 2.5 and it results to a short circuit current of 100 amperes. An EMF of 500 volts is produced on open circuit by the same excitation. The armature resistance is 0.8 ohm. So we are going to solve the voltage regulation at unity, 0.8 leading power factor and 0.71 lagging power factor at these parameters. So we have synchronous impedance will be equal to EOC, or the open circuit voltage, which is 500 volts divided by the short circuit current, which is 100 amperes, that is 5 ohms. And solving now, the XS is equal to the square root of 5 squared minus 0.8 squared. 0.8 is the armature resistance of the alternator. That is 4.936 ohms. Now, at unity power factor, of course, our power factor is equal to 1. Therefore, the load current will be 100 angle 0. This means that the current and the voltage are in phase. So if we draw the phasor diagram of this, our I and V are in phase and the voltage drop across the armature resistance is also in phase with the current. So nandito siya, and then the voltage drop at the synchronous reactance is 90 degrees with respect to IRA. So the sum of IRA and IXS is your IZS. Solving now your EO, that is V plus IZS. V is 100. Oh, wrong. IZS, the drop in here, IZS is equal to 100 ohms angle 0 multiplied by the synchronous impedance. Kailangan natin yung magnitude and direction. So, pwede rin na yung 5 lang, pero hindi mo kasi makukuha yung direction kung 5 lang yung isa-substitute mo dito na Z. So, we need the resistance and the reactance, 0.8 plus J, 4.936. So, the drop in the synchronous impedance now will be 500 angle 80.794 volts. So, EO now will be equal to 2000 angle 0 plus 500 angle 80.794 volts. So, EO will be 2,137.765 angle 13.3 349 degrees volts. Solving for the percent voltage regulation, that is EO minus V divided by V, that is 6.888%. So, nandito yung angle, 13.349. For the leading power factor of 0.8, of course, we need to solve the angle theta. So, that is arc cosine of 0.8, 36.87. Since this is a lagging power factor, so positive yung angle natin ng current. 100 angle 36.87. Our reference is here and it is in phase with the voltage. Since this is a leading power factor, so nandito yung current natin and also here. IRA, IXS, and the sum of these two will be IZS. This is Z, not XS. So, EO will be V plus IZS. Solve muna natin yung IZS. So, that is 100 angle 36.87 times 0.8 plus J 4.9361 equal to 500.05 angle 117.664 degrees voltage. So, EO now will be 1,822.466 angle 14.065. So, nandito yung 14.065. So, percent voltage regulation is equal to 1,822.466 minus 2,000 divided by 2,000 times 100, that is negative 8.09%. Next is the lagging power factor of 0.71. So, arc cosine of 0.71 is 44.765. Therefore, our current will be 100 angle negative 44.765 degrees ampere. Getting the drop at IZS equal to 500.051 angle 36.029 degrees volts. Just multiply the current and the synchronous impedance. Our EO now is the sum of the terminal voltage plus the drop in your synchronous impedance. So, EO will be 2,422.324 angle 6.974 degrees volts. So, this is the vector diagram of a lagging power factor. Nandito yung I, lagging. Also, the drop in RA and 90 degrees, the drop of IXS. Percent VR now will be 2,422.324 minus 2,000 divided by 2,000 times 100. That is equal to 21.116%.